Welcome back, everyone. So today we are going to start the Chapter 9 lecture note outline, so you'll want to have those available to you as we go through. And in Chapter 9, we are going to start looking at the chemical bond. So up until now, we've been looking at chemical reactions. We've been looking at just the basic mechanics of what's happening, and we haven't really gotten too much into how it happens. That's because we didn't have any real understanding about the actual forces that hold atoms together. And that's what we're going to be talking about in this chapter. So you're going to learn about the forces which allow atoms to be connected to one another in some way. And we'll learn about those two forces, the ionic force or the ionic bond and the covalent bond. And we're going to learn about what causes those, what the differences are between those, and that will help us understand more in a more intricate way how chemistry and why chemistry does what it does, and it makes some sense out of it. As we go through that and we learn about the chemical bond, we'll also start to learn about how we can look at a formula and turn that formula into a structural model for molecules. So the chemical bond, learning about it, we will get quite a few new tools at our disposal. So let's get started talking about the chemical bond. Now, to understand what makes atoms come together and form a bond, we're going to start by trying to understand what makes an atom more stable. And it turns out we have something called the octet rule, which we're going to discuss here in part 1. Now, what is this octet rule? Well, the octet rule refers to, when we say octet, we refer to the number 8. And what we're really talking about is 8 electrons. And it turns out the octet rule is more of a guideline, but it says basically that when you have 8 electrons in the valence shell for an atom, that's stable. That's particularly stable. And that atoms will seek out this configuration, these 8 electrons, to become more stable. So if you have just an atom floating around, it doesn't have 8 valence electrons, it's going to do something in order to get these 8 valence electrons. And where this sort of comes from, these 2 bullet points explain, is that this octet rule is that we've seen that when you have a full shell of valence electrons, so the shell outside of it doesn't have any empty spaces, and all the electrons are paired up, that is particularly stable. And we've seen that happens most often when you have 8 electrons around on the outside. This is like when we look at noble gases. If you look at noble gases, they have 8 electrons in their valence shell. They're in group 8. And you look at their electronic configurations, and the shell is full. So these two things are kind of one and the same. When you have 8 electrons in the valence shell, it's stable, and that also looks like all the electrons are paired. There are no empty spaces. So something about having that full shell and 8 electrons makes atoms particularly stable. And we're going to see if we can sort of use that to predict what atoms are going to do when they're around other atoms. What kinds of behaviors will we kind of see from them? So we call this 8 valence electrons, we call that an octet of electrons, and that atoms will generally follow what we call the octet rule, where they will seek out to have 8 electrons in their valence shell. So let's see how this octet rule works with some real examples, and we'll first look at metals, and then we'll look at nonmetals. So to understand what metals do when they are seeking to achieve a noble gas configuration, it's helpful for us to first look at the periodic table and notice where the metals are positioned, compared with nonmetals and compared with the noble gases. So let's write a few notes on a periodic table, which feel free to write this on your periodic table or just kind of watch as I try to explain this to you. So I'm going to show, first off, where are the metals compared to the nonmetals and where are the noble gases. So of course, noble gases are over here in group 8. So we start with helium and we go down to xenon. These are the noble gases in group 8, and they're in group 8 and they also have 8 valence electrons. And as we were discussing, the octet rule says that elements, whether they're metals or nonmetals, will seek to achieve this noble gas configuration. Now, metals are located over here on the periodic table on the left, and nonmetals over here on the right. Now, as I mentioned, when an element has the same configuration of electrons around it that it has with a noble gas, it's in a particularly stable state. So If we think about, say, for example, a fluorine atom, right? A fluorine can be in a noble gas configuration just by having one additional electron. If fluorine has one additional electron, it would have the same noble gas configuration as a neon atom. So it only has to gain one electron to do that. And if it does so, it becomes a fluoride, which has a -1 charge. That's because it gains one electron to do that, right? Now, why doesn't it become a helium instead of a neon? For as far as electronic configuration goes. Well, you think about this, like it can gain one electron, or fluorine could lose 1, 2, 3, 4, 5, 6, 7 electrons, and it would become a +7 ion. We know fluorine tends to form either the neutral fluorine or -1 fluorine. That's because the nearest noble gas configuration is just adding one electron. There's less energetic cost for fluorine to add one electron to its valence shell than it is to lose 7 entire electrons to become like helium. So we can say that the nearest noble gas to an element is the configuration of electrons that it will take on when it becomes most stable. So oxygen, for example, would become like neon rather than like helium or like argon. The closest noble gas to it is 2 spaces away, or gaining 2 electrons. So let's make a little note here, up here, that when we move on the periodic table in this direction, we're adding electrons to the configuration. If we're moving in this direction, we are taking away electrons from the configuration. So now if we look at some other elements, say something like aluminum, for example. Aluminum is over here in group 3. Now let's look at what aluminum would do. Aluminum is a metal, as we know. Now, is aluminum going to become a full shell? Is it going to add electrons to become like the noble gas argon? Or would it lose electrons to become like the noble gas neon? Well, to figure that out, let's just count how many electrons it would have to add to become like argon. So let's say 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons. So if aluminum gained 5 electrons, it would have the configuration of an argon noble gas. Now, what about neon? Well, let's see. If aluminum were to become like neon, and notice that it would have to lose 1, 2, 3 electrons, right? 13 and 10. The difference between those is 3. So if it lost 3 electrons, aluminum would become a +3 ion. And if you think about it, that makes more sense, right? Is it going to lose 3, or is it going to gain 5? Well, there are less electrons to lose if it loses 3 than there are to gain 5. And that's what metals do generally. So metals, you'll remember, are the boundary between metals and nonmetals is over here. The reason for that is that metals have a tendency to lose electrons because they're farther away from the later noble gas and closer, essentially, to the previous noble gas. So they tend to achieve electron configurations of the previous noble gas, and they do so by losing electrons. So let's write all of this down, and then let's look at an example writing out all of the electrons for aluminum. So how the octet rule works with metals is that metals lose electrons, right? They lose some number of electrons to achieve a noble gas configuration. And the noble gas that they're sort of going to mimic as far as their electrons go is the electronic configuration of the previously occurring noble gas. So the electronic configuration of the noble gas at the core of the metal, right? Rather than gaining electrons to become like the next noble gas, they lose electrons to become like the previous noble gas. That's what metals do. So they lose electrons. And we know that makes sense because metals tend to be cations, not anions. So they're always losing electrons. Now, what I want you to do is pause the video and write out the electron configuration for aluminum. And that's just neutral aluminum, just the regular atom. So to do that, of course, you're going to have to figure out what orbitals are present based on what row aluminum is in. and then fill the orbitals up with the right number of electrons for aluminum. So to figure that out, look at the periodic table, look at the atomic number for aluminum, and if it's neutral, it will have the same number of electrons as it does protons. So go ahead and do that and then unpause the video, and I'm going to write out that electronic configuration here so you can just double check that you're getting that right. So if we look at aluminum on the periodic table, you'll see that it is in row 3. So it has available to it the s and the p orbitals at rows 1 and 2, and then the s and the p at rows 3. And it only has 13 electrons, so we're not going to have any d orbitals, although they are available to it. Now, this is the electronic configuration. It's 1s2, 2s2, 2p6, 3s2, and 3p1. The core electrons are down here at the lower principal quantum number, and then the valence electrons, the outermost ones, are here. Another way of writing this out would be the shorthand configuration, where we write out the noble gas core. And if you look at aluminum on the periodic table, you'll see that the noble gas at its core is neon. So we can write bracketed neon, and then the valence shell on top of that, which is the 3s2, 3p1. So there are 3 valence electrons above a neon core. Now, what we're going to do next is look at what happens to aluminum when it ionizes. What charge will it have? So let's first off, what does aluminum do when it becomes charged? Well, we've learned that aluminum is a fixed charge metal with a +3 charge. So if we go from aluminum neutral and then we draw like what would it ionize to? So we can represent that with a forward arrow. We would have the aluminum 3+. And we know this is the most stable ion for aluminum. Now let's write out the electron configuration for this aluminum 3+ cation. So what I want you to do is now write out the electron configuration for this aluminum 3+, which is obviously going to be different than the neutral aluminum. Write out the electron configuration for that. So with 3 less electrons, what that means is that we're going to take electrons from the highest energy orbital. We're going to take 3 of them out. And we know that the highest energy electrons at the highest end of the energy scale are these valence electrons, the 3s2 and the 3p1. And if we take 3 out of there, that means the valence shell would be completely gone and we'd be left with just the core electrons, which of course is the noble gas neon. So that's basically what we're talking about here, is that when metals lose electrons to become like the previous noble gas. In aluminum's case, that happens to be neon. Let's take a look at another example. Let's look at calcium. So what I want you to do first is write out the electronic configuration for a neutral calcium atom, and then we're going to go through and look at what happens when it ionizes. Let's look at the charge that it should have, which is +2, and let's write out the configuration for that as well. So if we write out the electron configuration for calcium, we see that it's down in the 4th row, so n is equal to 4. So we have to fill up all of the available orbitals up till n is equal to 4. And we see that we have this core set of electrons, which is identical with the electronic configuration for argon, and then there are 2 electrons in the valence shell, the highest energy electrons. Now, we could also write this out as a shorthand with bracketed argon 4s2. That's fine. And in some ways, that's a little more clear, right? And it shows you what is possible if calcium were to lose the 2 electrons that are sticking out of this argon configuration. If these would go away, we would be left with a really stable noble gas core. And that's exactly what calcium does, is calcium ionizes by losing these 2 electrons to achieve an argon electronic configuration. So it can kind of masquerade as an argon instead of having these 2 electrons kind of sticking out over it. So if we go to this next one, it says when calcium ionizes, what charge will it have? Well, as we know, it's in group 2, and everything in group 2 forms a fixed charge +2 ion, and that would also be the same for calcium. So calcium forms a 2+ cation. And if we write out the electronic configuration for this, it's just basically bracketed argon, right? That's the electronic configuration for it, because it lost 2 electrons. So it's like if we wrote this out as a kind of a reaction arrow, we would see calcium neutral, and then it would lose 2 electrons to become calcium 2+. And Calcium 2 plus has this electronic configuration, the same as argon. Okay, so that's the basic idea. Take home with this is that metals lose electrons to get a noble gas configuration, but guess what? Nonmetals gain electrons to become a noble gas configuration. So nonmetals become anions, as we've learned, and metals become cations, also as we have learned. Let's go on to the next page and look at a few other things. So as I mentioned on the previous page, is nonmetals gain electrons to achieve a noble gas configuration, so they become anions when they gain electrons, whereas metals do the exact opposite. They lose electrons, become cations. So what we're going to look at next is how this works with nonmetals. And what I want to show you is, I want to show you metals and nonmetals together at the same time, showing how metals will lose electrons, and they lose them to nonmetals. Nonmetals gain them, so nonmetals will gain electrons from metals, and they both are doing this at the same time to achieve noble gas configurations. And this first example I want to look at is when we have magnesium and oxygen together. Now, magnesium and oxygen so if you combust magnesium, it will burn and form magnesium oxide. So the compound that you get from magnesium and oxygen together has the formula where we have one magnesium and one oxygen together. And we've learned through charge balancing that this is like a magnesium that has a 2+ charge together with an oxygen that has a 2- charge, and we needed one of each so that the charges balance out. Now, this is happening because magnesium is losing 2 electrons and oxygen is gaining 2 electrons, so that both can achieve a noble gas configuration. And that's exactly what we're going to look at now, is sort of what's going on with the electrons at the electronic configuration level. So what I'm going to do is I'm going to write the noble gas shorthand for magnesium neutral and oxygen neutral, and then we're going to see how they change when these two things transfer electrons between each other. So let's look first at the before picture. Like we just have, before anything happens, we just have magnesium and we just have oxygen. And let's write out their electron configurations before anything happens. So magnesium is neon at its core with 3 s2 valence electrons. And then we have oxygen, which is helium at its core, and its valence shell has 2 s2 and 2 p4 configuration. So notice for oxygen that there are 6 electrons in the valence shell. So we have 6 valence electrons. Also notice that neither of these has an electron configuration for noble gas, right? So the nearest noble gas for magnesium is neon if it could lose 2 electrons. But the nearest noble gas for oxygen is if it gains 2 electrons, right? It would be like a neon configuration. So, and also notice, like in the same measure, that if these 2 electrons around magnesium were in the valence electron configuration for oxygen, both of these 2 atoms could then have a noble gas configuration. And that's exactly what happens. So let's look at the after picture where we move the 2 electrons from magnesium to oxygen's valence shell. So let's write all that out. So we're going to take these valence shell electrons from magnesium and transfer them over to oxygen. That way, magnesium will have a noble gas configuration and happens to have a 2+ charge, and it resembles neon as far as its electrons are concerned. And then oxygen gains those 2 electrons. So its new configuration is going to have 8 electrons in the valence shell. So 2 s2 and 2 p6. Notice this adds up to 8 valence electrons. Now, if we look at what element that is, it's the next noble gas, which is neon. So by doing this transfer of electrons, we've sort of killed 2 birds with 1 stone, right? We've given magnesium and oxygen both the noble configuration of a noble gas that it is closest to, right? So magnesium loses electrons, oxygen gains them. Okay. This what I've just shown here is the process of something called an ionic bond forming, where we transfer electrons from a metal to a nonmetal. This is called ionic bonding. And when we draw them out, we usually show this where we have the two ions in brackets. So we have magnesium, which has a 2 plus charge, and then we have oxygen, which has a 2 negative charge. And then we usually just draw these next to each other. What's holding these two together is the fact that they have opposite charges. Just like magnets, it's an electrostatic attraction between these two. This force that holds these two ions together is called the ionic bond. And it's an electrostatic force that is occurring between two oppositely charged ions. And that's why we call it the ionic bond. Bond meaning holding two things together, and ionic meaning charges. Okay, so that's what happens when we have metals interacting with nonmetals. This also can happen between two nonmetals, except we don't get an ionic bond, it turns out. We get something called a covalent bond. Now, before we go into, I'm going to show you how this works with chlorine gas. But before we do that, what I want to do is show you, notice that this little method that I was showing here, it's very cumbersome, showing all of these, writing out all these electron configurations and the noble gases. Really what we're doing, if you boil it down to the most basic thing, is that we are showing how the valence shell is changing. And we're looking for valence shells that are completely full with 8 electrons or completely empty, like with metals, right? So that's basically what we're looking at. Now, there's a nice, simple way of doing this, and we're going to use this quite a bit. It's called Lewis dot structures. And this was developed or invented by a chemistry professor at UC Berkeley back in the early 1900s. His name was Gilbert Lewis. And he came up with this method for showing how this worked by kind of fiddling around with things. And he came up with something we call Lewis dot structures, which is essentially what we do is we use the symbols of the letters as we've been doing, like H is hydrogen, lithium is lithium, and C is carbon, and N is nitrogen. And then we use little dots to represent represent electrons around atoms. So dots represent electrons, and then the symbols represent the atoms. And what we're showing here specifically for the electrons is just the valence electrons. So notice in group 1 for hydrogen, we have 1 valence electron. This is group 1 up here. And notice that all the group 1 elements have 1 valence electron. So sodium should have 1 valence electron, and potassium should have 1 valence electron. And then if we go over to group 2, we have 2 valence electrons. So beryllium has 2, and then we would have 2 for magnesium, and we would have 2 for calcium. And then we're going to jump over the transition metals because they are complicated. We're not going to be doing those in this class. But if we go back over to the other side of the periodic table, where we're over here in group 3, where we have boron and aluminum, we have 3 valence electrons. So boron should have 3 dots, and aluminum should also have 3 dots, like that. Okay, we can continue with this. Silicon, just like carbon, would have 4 valence electrons, and then nitrogen would have 5. Now here's where, when we're showing them, there's a little bit of a method to drawing this. Now, the way it works out is, I'm going to draw a little X down here, is we have 4 sides. So there's a side on the top, the bottom, the left, and the right. And we can have electrons in each of these places. So we can have 1 electron, or we can have 2 electrons. That's the most we can have on any given side. So you can have 1 electron or 2 electrons, like this or like this, right? So this would be an octet that I've shown here, okay, where all of the sides are full. Now, the way we're going to do this to help us out is we are going to, just like when we follow Hund's rule, when we're writing out the electronic configurations, is before we pair electrons up, we're going to place them singly around the sides first. So let's do nitrogen. So we're over here in this was group 4 for carbon, and then nitrogen is group 5. Okay. So group 5, there are 5 valence electrons. So how many dots should hydrogen have? That's correct, it should have 5. So let's place the 5 electrons around nitrogen. Now what I'm going to do is I'm going to arbitrate. It doesn't matter which side I picked. So I'm just going to pick the top first. So that's 1 electron. Then we get 2 electrons. Notice I didn't pair them up. And we get 3 electrons, and then we get 4 electrons. So I have 4 electrons, and notice I've placed them all alone first. I haven't paired any up. But now we have to do the 5th electron. So the 5th electron has to be paired with one of the others. And it doesn't matter which side I pick. You're going to see later that when you're drawing things on paper, you'll naturally want to pick one side versus another just for drawing purposes to make it look right. So I'm just going to arbitrarily pick a side for now, though. I'm going to put the 5th one there. But you could put it really any of the other sides as well. That would be fine. Okay, so that's nitrogen. Phosphorus, it's also 5 electrons. So it will have exactly the same Lewis dot structure as nitrogen because it has 5 electrons. Now let's go do oxygen. Oxygen is in group 6, right? So it has 6 valence electrons. So let's put the dots around oxygen. Okay, so we're going to have 4 that are unpaired, right? And then we're going to start pairing them. And again, it doesn't matter where you start and where you end. I'm just going to start over here. So that's the 5th electron, and then this is the 6th electron. It doesn't matter which side. So here's sulfur. 1, 2, 3, 4, and then 5 and 6, right? Notice they look different. Chemically, though, they're exactly the same. It doesn't matter which ones are paired, which ones are unpaired. As long as we show that there are 2 paired and 2 that are unpaired, okay? Let's do fluorine and chlorine. These are in group 7. Okay, so there are 7 valence electrons here. So let's draw those 7 valence electrons. 1, 2, 3, 4, and then 5, 6, and 7. Okay, let's do chlorine. 1, 2, 3, 4, 5, 6, and 7. Great. Now we're going over to the noble gases, and the noble gases are in group 8, so they should have 8 valence electrons, with the exception of helium. Helium, like hydrogen, those are kind of interesting elements because they're in n is equal to 1. So they only have s orbitals available. Now, helium also only has 2 protons in it, so it will only have 2 electrons. So we're not going to have 8 electrons in helium. We're only going to have 2. So when we place the dots, we get the 1 and the 2 here. Let's go down to neon, right? Neon is in group 8, and it will have 8 valence electrons, okay? So let's place those 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, and 8, okay? Argon, also 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. Now, I just did those as pairs, but I was kind of going as a shortcut. Now I'm going to show you doing them one at a time. 1, 2, 3, 4, and then we have 4 more. 1, 2, 3, 4. Now, let's take a look at these different things. You might notice some trends here. First of all, notice that when we have a full shell, an octet of electrons, notice that there are no empty unpaired electrons on these. All the electrons are in pairs, and we have a maximum of 8, so that's full. So if we look at the noble gases like neon and argon, notice there's no place to put anything else. All of the spots are full. But that's not the case for all of the different elements, right? That's actually not the case for most of the elements. So for instance, if we look at group 7, fluorine and chlorine, how many spaces are there available to have another electron? Well, notice that fluorine and chlorine both have 1 space available to them. We're going to learn that that means that we can make fluorine and chlorine will make 1 bond because we have 1 space available. Notice that for oxygen and sulfur, there are 2 spots available. And we're going to learn that oxygen and sulfur form 2 bonds normally. We're going to see what that looks like. Nitrogen has 3 spots available and forms 3 bonds. So does phosphorus. Okay. Carbon, famously, can form 4 bonds. That's the basis of organic chemistry, it turns out. Silicon does the same. Aluminum, 3 bonds. sometimes it's a metal, so it's not bonding the way the non-metals do, but it has a space here, a space here, a space here, but it also has this space here if it formed covalent bonds, which it doesn't. Anyway, when we get over to metals, things are a little bit different. As we'll see, metals do things that are a little bit funny. But anyway, for non-metals, those little empty spaces there are predicted places where we can have electrons and we can do things in those spaces. So there's nothing available in the noble gas column because those are completely full shells, but that's not the case for groups 4, 5, 6, and 7. All right, so that's Lewis dot structures. It turns out they are very, very handy for being able to predict the way that atoms behave and how they react. So I'm going to show you Lewis dot structures for chlorine gas. Now, chlorine gas is a diatomic chlorine, so it has 2 chlorine atoms. And if we look at chlorine, right, I'm going to look at 2 different chlorine atoms. Chlorine is in group 7, so it has 7 valence electrons. So let's put those 7 valence electrons around chlorine. I'm going to use red for this. So we get 1, 2, 3, 4, and then we're going to have to start pairing them. So 5, 6, and 7. Now, I intentionally chose those to be paired rather than the one facing the other chlorine, because it turns out that's where the interesting stuff is going to happen with the other chlorine. Let's do the same thing with this chlorine. So we got 7 valence electrons, 1, 2, 3, 4, and then 5, 6, and 7. Okay, so these are 2 Lewis dot structures for individual chlorine. Now, the thing about nonmetals is, instead of giving electrons or transferring them to and from each other, they end up sharing electrons. Nonmetals share electrons with other nonmetals to achieve a noble gas configuration. Now, notice that each chlorine needs 1 electron, so 1 electron each to have 8 electrons, right? So each chlorine right now only has 7 electrons. And if each one had 1 more electron, they would have 8 electrons each. Now, we can't give 1 electron to the other because then we'll be losing, both won't have a noble gas. So this is what nonmetals do, is instead of transferring them, they share them together. So I'm going to draw a little forward arrow here. And you can imagine sort of one of these chlorine atoms moving towards the other one, and this one moving towards the other one, and them getting close together and end up sharing the electrons between them. So we would have a chlorine and then a chlorine, and they're much closer together now. They get closer together so that the electrons are shared between them. So there's this one and this one being shared like this. Okay, so those are shared now. Now, if we count up all the electrons around them, it's like they're cheating a little bit in order to get 8 electrons. It's like, hey, I've got $1, you've got $1, let's go buy a candy bar together. And that's what they're doing. They're sort of going off together now with 8 electrons each. So let's write that, 8 electrons each for both of these chlorine atoms. So there's no way to say that each one doesn't have 7, 8 because they're sharing them between them. Now, this is called, this little thing here, this sharing of electrons, this is called a very important thing. It's called a covalent bond. Covalent means between the 2 valence shells. And it's a bond, meaning that they're sharing electrons between them. And a covalent bond is the sharing specifically of 2 electrons. That's what a covalent bond is. And we know that orbitals can only have 2 electrons maximum in them. And that's what a covalent bond is. It's actually an orbital of electrons that the 2 atoms are sharing between each other. And you can have a maximum of 2 electrons in it. Okay, now we normally draw this covalent bond as a single line between the 2 atoms, which I'm sure you've seen before, actually. The way we usually draw this is without the dots. We usually show the 2 atoms next to each other, and of course they have their lone pair electrons that aren't bonding. These are called non-bonding electron pairs. But then between them is a covalent bond, which we usually just draw with a line, okay? So that is also a covalent bond. That's normally how we draw it. All right, so that's a lot of information about Lewis dot structures. Let's go and look at a few other examples on the next page. So now that we've learned what a Lewis dot structure is, let's revisit this idea of what an ionic bond is versus a covalent bond, and let's use Lewis dot structures to show what's going on. So let's look at the first example here, which is sodium chloride. So we've got a sodium atom, and we've got a chlorine atom. So I'm going to draw the chlorine right over here. And let's put the electrons in as dots. So I want you to pause the video and write the electron dot configuration for sodium and one for chlorine. So if this is what you drew, great job. We have sodium here, which is in group 1. And because sodium is in group 1, it has one valence electron, which you can see is the purple dot there. That's our valence electron for sodium. And then chlorine is in group 7. So it's in group 7, it will have 7 valence electrons. So this is the electronic configuration for sodium and for chlorine. Now what an ionic bond is when we transfer electrons from a metal to a nonmetal, where the metal loses the electron and the nonmetal gains it. They do this so that they can both achieve a noble gas configuration. So if we look at sodium, it has this extra electron in its valence shell. It could just get rid of that. If it just got rid of that, it would have a noble gas configuration. It wouldn't have any extra electrons on it. Meanwhile, the chlorine needs an electron so that it can have a full shell of electrons. So this is exactly what happens. I'm going to draw a forward arrow here representing sort of the change that goes on. And what an ionic bond is specifically is, again, it's this transfer of the electron from the sodium to the chlorine atom. And by doing this transfer of the electron from sodium to chlorine, chlorine can get the noble gas configuration, though it does become an anion, and sodium can also achieve a noble gas configuration, becoming a cation. So we end up with a sodium plus 1 cation and a chloride 1 negative anion. And because of this, we have an ionic bond between these two charged species. So that's basically what an ionic bond is. Now, you've seen examples of ionic compounds where there is more than one nonmetal, and sometimes more than one metal also. Let's try an example like that. Let's take a look at magnesium chloride. So first off, let's write out the formula for magnesium chloride. Magnesium chloride involves magnesium, which we know to be the 2+ cation when it ionizes, and we have chloride, which is the -1 anion. For this to be charged balanced, we need to have 2 chloride anions to give us the 2 negative charges we need to balance with the 2 positive charges from magnesium. This is in order to make a neutral compound. So the formula for magnesium chloride is 1 magnesium and 2 chloride anions. Now let's take a look at what this looks like as far as the Lewis dot structures are concerned. First off, magnesium is in group 2, so it has 2 valence electrons, which I'll represent with the 2 dots I've shown here. And then we know chloride has 7 valence electrons, which I'll show as such. So we have 2 of these chlorides and 7 dots around each of them. Now we have these 2 electrons on magnesium. These are extra electrons on top of the noble gas configuration for magnesium, which if you look at the periodic table, the previous noble gas is neon. So it's basically like neon electrons at its core with these 2 extra s electrons in its shell. So we need to get rid of those, and we can conveniently give them up to each of the chlorides. So one of these electrons can go here, and the other one can go over here. And when we do that, we can see how what the ionic forces involved here are. So what we've got is magnesium, and that has no electrons around it anymore. It lost 2, so it's 2 deficient, giving it the 2+ charge. And that will form an ionic bond with the chloride anions on just drawing them on opposite sides here, which have all 7 electrons around it now. And each of those, because each one gained 1 electron, each one is a -1 charge. So this is the ionic bond that we have going on here. We have the magnesium, 2 plus, the chloride, which is each of them is 1 minus, and then we have the ionic bonds, which I'm showing here. These are the ionic bonds. Now, ionic bonds, again, those are just the forces, the electrostatic attractive forces between oppositely charged ions, right? Ions with the same charge will not form an ionic bond. Like a magnet won't stick to another magnet if they're at the same pole. They have to be opposite poles. So that's the ionic bond. Now let's talk again about the covalent bond and show that as well. As I mentioned earlier, covalent bond is the sharing of electrons. Rather than the full transfer, it's the sharing of electrons. And that occurs when we have two nonmetals bonding together. They do this to achieve a covalent bond where both have a noble gas configuration. Let's take a look at how this works with the example of hydrochloric acid, or HCl. So the first thing we're going to do is write the Lewis dot structures for both hydrogen and chlorine. Hydrogen is group 1, so it has 1 valence electron and 1 dot, and chlorine is in group 7, so it has 7 electrons, or 7 dots. Now if you notice that each one of these can share that electron with the other, and by doing so, they both achieve a noble gas configuration. Hydrogen can achieve 2 electrons, which is the same as helium noble gas. And then chlorine can have 8 valence electrons, which would have the same for chlorine, would be the noble gas would be like argon. Now this sharing of electrons is 2 electrons being shared. We call that a covalent bond. And I'm showing you an example where we're sharing just 2 electrons at a time. Specifically, we call that a single covalent bond, or a single bond. So just summarizing that, we show the sharing of electrons. When we have a pair of electrons, we show that as a single line. This represents a single bond. Now, we will see later on that it's possible to have double bonds as well as triple bonds. We'll focus in this class on single and double bonds. But in those cases, we have more than one line between atoms, and I'll show you how that works later on. Before we move on to that, though, let's look at another example where we have single bonds. And this is one where we're going to have more than one nonmetal forming a molecular compound, and we want to find out where all the bonds are. So we're going to look at methane, which has the formula of 1 carbon and 4 hydrogen atoms. And I want to show you how that works as far as the Lewis dot structures are concerned. So methane contains the elements carbon and hydrogen, and we know carbon is in group 4, so it has 4 valence electrons, and hydrogen is in group 1, so it has 1 valence electron. And we're going to see why methane has the formula CH4 if we consider both of these elements sharing electrons with each other to form a noble gas configuration. So if we think about how this works, let's imagine for a minute that there was 1 carbon atom with its 4 unpaired electrons, and then we had 1 hydrogen atom. What can happen here? Well, we can pair up on each of these the unpaired electron, and that stabilizes it by filling up that orbital with 2 electrons. So if we put the hydrogen here, for example, that would be a paired up electron, and that's 1 bond to that carbon. Now, notice that carbon can still, or I guess more than can, but needs to have 3 more electrons in its valence shell to complete the octet. We have an unpaired electron here, here, and here. And that means we can make 3 more bonds, which means 3 more hydrogens can share electrons. So we can have a hydrogen here sharing an electron, a hydrogen over here sharing an electron, and a hydrogen down here sharing an electron. So we have, if we add up all of these, or we look at all of these, there are 4 sets of covalent bonds here. So we have 4 covalent bonds. And those 4 covalent bonds are just 4 single bonds because it's the sharing of 2 electrons between one atom and another atom. So we have 4 single bonds. We can redraw this with the lines representing each of the bonds. So we have carbon in the middle, and then we have a line going out to each of the 4 hydrogen atoms. And this is the Lewis structure for methane. So we're going to stop the lesson here today, and next time what we're going to look at is what are double bonds and how do those form? And then what we're going to do is we're going to learn something really, really neat, something interesting. We're going to take this information we have about Lewis dot structures, And then we're going to use the Lewis dot structure and the molecular formula to predict the three-dimensional geometry of the Lewis dot structures that we draw. So you might notice here that these Lewis dot structures I'm drawing are all two-dimensional, or they're all flat, basically. We're going to add the third dimension into this, and we're going to look at what predicted shapes we can get when we look at the configuration of electrons around atoms. So that'll be what we learn next time. It's called valence shell electron pair repulsion. So yeah, next time we will learn about valence shell electron pair repulsion. You will also have a chance to practice that in a lab that we have planned for you, a lab exercise. And with that, I'm going to end the video. Please let me know if you have any questions, and I will see you soon. Take care.